Okay, so let's talk about something deep, right? We know that when we look through our telescope, we see a universe of very interesting kind of things on all kinds of scales. On the smaller scales, we see planets and moons. On the larger scale, we see stars, galaxies, clusters, blah, 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 blah. A whole range of different things. It seems like the universe has a big, wide bucket of different kinds of objects in there. Now, I know you've been given a talk to sort of simplify this kind of picture on why we see what we see in the universe in relation to fundamental physics. So do you want to take us through this?
So here's the idea. When you're an astrophysicist, you want to try to understand what we see in terms of the physical forces that move stuff around. And so if we see something in the night sky that seems pretty stable, right? It was there last night. It'll be there tomorrow night. It's probably been around for quite a while, then it must be stable in some sort of physics way. The forces acting on it must balance in one way or another.
Okay.
And so the question we can ask is, okay, one of those forces for astronomical things is always going to be gravity, right? Because that's kind of the definition of an astronomical thing. If it's big enough that its own gravity, the gravity of itself, matters. And so if gravity for ordinary matter and for dark matter as well is always attractive, always pulling the thing in, then there must be something, if we've got something stable, which is balancing that force and holding gravity at bay so that the thing is not totally collapsing on itself.
Okay.
And we can ask that question of the different things in the night sky.
So which way should we work? From small to large or large to small?
Well, let's go from small to large.
So planets.
So planets. So the first thing that we can think of, which might sort of hold its own against gravity, is just the ordinary hardness of matter. So there's atoms in this whiteboard, and they have their own structure they're holding together. And so when I try and I hit the board, it has its own sort of rigidity and it will hold back. And so what we can find is, let's ask, how big does something need to be before its own gravity is about of the same strength as its own internal atomic forces to hold it together? And on the lower end of that scale, you have asteroids, which are big, but they can be slightly wonky shaped. As you make a bigger and bigger rock in space, which is basically what an asteroid is, the force of gravity is going to start to crush it into a sphere.
Why a sphere? This is a question that lots of people ask me. Why are planets spheres?
Well, let's imagine that you have some sort of mountain, right? Mm-hmm. That's very easy to imagine because we do. So you're building. Let's imagine you're building, say, a sandcastle at the beach. As you start to pile more and more and stuff on top, the stuff up the top starts to crush the stuff underneath. And so there's some limit when you've got sand of, if I make this thing too thin and too tall, it'll not just fall over, it'll crush itself. The sand at the bottom won't hold the stuff up at the top, especially if it's, say, dry sand or something. All right, so now let's do that with rocks. How big does a mountain need to be before the weight of the top of the mountain crushes the stuff at the bottom? And it'll basically sort of liquefy that stuff. And the answer is, for something the size of Earth, bigger than the mountains we've got, but not much bigger. And so what that's telling you is, if you have any shape that's not a sphere, its own gravity will crush any sort of deviation away from perfect roundness back towards roundness.
Yeah. And
so the equilibrium state there, once again, when those forces balance, is when things are round, so that everything's pushing in the same direction, and any sort of lump on the side of the sphere gets crushed back towards perfect roundness. And so you can look at what's the size something needs to be before it'll basically crush itself into roundness, and that's sort of the smallest size of a planet. And we can see smallish planets, so even dwarf planets. So something like Pluto is kind of on the edge of that. It could handle a bit some relatively large mountains, but anything much larger than that, say the Earth, we've got relatively small mountains compared to the size of the Earth.
Does this set a limit on how big a rocky planet can be?
Yes, and up the other end, let's now just make things bigger and bigger and bigger. There's a point at which atomic forces are only so strong, okay? As you add, so each atomic force is only really, each atom in this board is only really connected to sort of the next atom over the next atom over. So making this board bigger doesn't make it stronger. So the atomic forces are only so strong, but gravity just keeps adding up and adding up and adding up and adding up. And there's a point which is sort of slightly bigger than the mass of Jupiter, at which we need another form of another force, another kind of force in the universe, not just atomic forces, to hold the thing up against gravity.
Okay.
So this is the transition from a planet to what's called a brown dwarf. So what's happening there is, and it's a little bit difficult to explain, but basically we're used to the fact that ordinary matter doesn't like being squashed. So if you try and squash this table, it'll fight against you. When you get matter where all of the quantum wave functions, all the quantum weirdness is starting to overlap with itself, and you start to get matter behaving like a quantum system, you get something called quantum degeneracy pressure. The way I like to explain this is matter doesn't like being squashed, and quantum matter really, really doesn't like being squashed even more than ordinary matter.
Okay.
So if you have something a bit larger than Jupiter, it will actually hold itself up as a brown dwarf against gravity by this quantum electron degeneracy pressure.
Okay. So Jupiter is the largest kind of planet that's supporting itself by its kind of internal normalish pressure. Normalish. Yeah. Brown dwarfs are now these things which have the electron degeneracy pressure. Mm-hmm. Keep piling matter on, what happens?
What happens, the next thing that needs to happen is the gas pressure, not just the pressure of a solid, but of gas particles moving around and bouncing off each other really quickly, like you would have inside a balloon, say. That actually, we can put gravity versus that pressure, and then what we've got is a sort of self-gravitating stable ball of gas, and that we call a star. Now, the problem with that is, in order to have a high gas pressure, you need a high temperature. And so for a given ball of gas, we can calculate without any question of nuclear forces or anything like that yet, we can say, how hot does this thing need to be? And if it's at a certain temperature, hot things glow, as we know, right? So you heat up a rod of iron and it starts glowing. That sort of ball of gas, we'll call it for the moment, will glow, and it'll glow like a star. That's basically what a star is. But because it's glowing, energy is leaving.
Okay.
And so if those were the only forces, the star would have to keep collapsing to get more and more energy, and actually stars wouldn't live particularly long.
How long would a star like the mass of the sun live?
This was worked out actually sort of the early 1900s, and it's in the millions of years.
So far too short to explain the sort of number of stars that we see in the sky. They must be stable for longer, and we already know from life on Earth the sun has been around for billions of years, not millions of years. So
this was a major, we didn't know how the sun shone until about the 1930s and 40s. We've covered this in a previous one of these podcasts. Well, it's a podcast now. We've covered this in a previous video, that it's nuclear reactions. That what happens is you can calculate how hot the center of the sun will get in order to support itself, and at those temperatures, nuclear reactions will happen. And so as protons get slammed together, eventually making helium, energy will be released, and that energy will replace the energy that's leaking out. And the whole thing is a sort of beautiful thermodynamic and nuclear equilibrium for this case of the sun, about 10 billion years.
Is it guaranteed to be stable? I can imagine that, you've got this, you have these nuclear reactions at the center of the star, of the sun. Mm-hmm. They're very sensitive to the temperature and the density. And you could imagine that the sun wouldn't have necessarily settled down to be a nice, stable, burning star, that it would possibly undergo oscillations and cycles, that you'd get bursts of energy, and the sun would basically be constantly combating gravity versus the other forces, but not in a stable way. Do we see unstable stars?
We do see unstable stars.
Oh.
So there's two bits of this. We do see stars which are pretty stable, but they have cycles. These are called the Cepheid variables. So there are stars which just get brighter and darker in the night sky as we look at them over the course of days or months. So there are stars, and they're sort of like there's sort of like a heat engine. So things will collapse a bit. The things will get hotter and denser. The nuclear reactions will fire up, and they'll push everything out because there's now more pressure, and then they'll cool off, and the whole thing will kind of oscillate in a quite obvious way, and where you can see the sun. Those oscillations, the way the sun is set up, and for most stars, those oscillations die off. And so actually the sun is remarkably stable. It doesn't undergo these rapid variations, these significant variations.
It would be an interesting question if we would have had life on Earth if the sun varied by, I don't know, 10% on timescales of days to months to years, right? But
well,
okay.
This is an open question for... There are smaller stars than the sun called red dwarfs, and they're very flary. They have the occasional episode. It's an interesting open question as to what that does to any planetary life around. But let me move on.
Moving up in scale.
Moving up in scale. So there's a limit to how big you can make a star. Actually, it's related to this oscillation issue. If you make a star really, really big, then it's so hot that there's not just the pressure of the gas inside it, there's also the pressure of the light bouncing around inside it. This is called radiation pressure. So light is made of particles. They will bounce off something just as the way that atoms will bounce off something. And that's a form of pressure. You could actually push something with light, right? The problem with that setup is the star now becomes less stable towards these oscillations. So a really big star... these oscillations could get totally out of hand, and the star will simply shed a whole heap of mass to get back down below the limit. It's about 100 to 200 times the mass of the sun. Okay. So the largest star we've ever seen is about 300 times the mass of the sun, I think. And it's sort of on the limit where if it ever underwent a bit of an episode, if something perturbed it, it could start oscillating and get out of hand and start throwing stuff into the universe. Even larger than that, there are ways you could set up a star with, say, 1,000 solar masses or 10,000. It would be very susceptible to these oscillations. And in particular, they all burn out very quickly. It's an interesting fact about stars, actually, that the bigger the star, the more fuel it has, but also the faster it burns. And so actually, that more than... It compensates for the extra fuel, and big stars burn out faster. And any super large stars, anything bigger than about 100 solar masses, 100 times the mass of the sun, burns out in sort of about 1 million years. And that amount of time, when you look at the history of Earth, is shorter than the amount of time it took the Earth to cool off from being just a molten ball of rock. So that's probably not particularly good for life.
Okay.
If you want to make something bigger still, it can't be one sort of coherent object.
Okay, so we know that if you put too much mass in a place, gravity eventually wins and things completely collapse. Right? So this is when we get into the realm of black holes, which I think we'll talk about separately, but eventually gravity wins and no forces can stop it. You form a black hole. But I think that's a separate topic. So we're now moving from the stage of having a single object to having groups of objects. Gravity still reigns, but you have other forces involved.
Well, it's not so much other forces as just motion itself. Motions. So think of the solar system, right? The sun has an awful lot of gravity, but the Earth isn't falling into the sun. Well, it kind of is, but it's falling around in a circle, so to speak.
Yeah.
So this is one of the interesting things about if you're in let's say the International Space Station above Earth going around, you'll be floating. But it's not that there's no gravity there. You're still feeling the pull of Earth. It's just that you're falling in a circle, right? You don't just fall straight down, you fall around. And the space station falls with you, so you don't fall to the floor of the space station. Yeah,
I'd just like to mention one of the memorable analogies that I have in my mind talking about space flight, right? And if you're an astronaut, what does being an astronaut feel like? It's that moment as you go over the top of a roller coaster when you're weightless and your stomach drops. That's what weightlessness is. Except it doesn't last for a fraction of a second. You're up there for months and you're constantly feeling like you're going over the top of a roller coaster.
I've horrified groups of people by mentioning this particular point. Everyone thinks it's going to be like swimming in air.
Yeah.
But it's amazing the human body can handle that for a couple of months. Just that, here we go. Yeah. This is life now.
Yeah.
Okay. So if things are moving in the right way, gravity, instead of making a thing collapse, will make it just sort of orbit.
Yeah.
So we can make solar systems that way. If you have that orderly kind of rotation that we see in the solar system, then you'll have things in a nice flat disk, things going around in a circle. And we can now scale that thing up, right? So the disk galaxies we see, like the Milky Way, they're stable for this reason. Roughly, all the stars are going around in sort of roughly circular orbits. And so that's how you can make a disk galaxy. But there's another way to make motion work for you to stop you collapsing. You could just have random motions. If everything's kind of buzzing around, feeling its own gravity as a ball, but everything's moving so fast that, yes, it'll fall towards the center, but then it'll go through and around the other side. You could just have a sort of random ball of stars, say. And so we see those in the universe. We see what are called globular clusters, which are just clusters of stars. There's no sort of obvious structure there other than it's a great big ball of stars, all feeling their own, everyone else's gravity. But because relatively stars are quite small, they all just sort of orbit around the center of the whole cluster, and that whole thing holds it together.
Is there a maximum size here with this buzzing around motion?
Well, not particularly. It depends what the universe can make. I guess there might come a point where actually you get into the black hole territory, but there's no obvious sort of problem there in the way that you can't make a star of a
So do we have
particular size.
galaxies that have similar motions?
Yeah, so we can do the same thing writ large in what are called elliptical galaxies. So for a globular cluster, they're part of a galaxy. So the Milky Way has a couple of them around. Typically, say, 10,000, 100,000 stars in a galaxy of 100 billion stars.
And I hear some ellipticals are trillions of stars.
Yes.
The really, really big guys.
So you probably haven't seen a picture of an elliptical if you're listening to this, because they're not particularly pretty. Whenever you want to put a galaxy in a calendar, you don't just pick some blob of stars. But we see these other types of stars out there. They're roughly as common as disk galaxies, and they're just a great big ball of stars moving randomly. There's also, because of that size, there's also dark matter in there. And that's the other way you can arrange stuff. We think dark matter is basically like, even for disk galaxies, is basically like these globular clusters, ellipticals. It's just a ball of randomly moving particles, which has stabilized itself because it's just in motion. But there's no interactions between in the globular clusters with stars, no interaction between the dark matter particles. And so it's just stable. It just stays there under its own gravity.
Okay. So we've got galaxies, right? So, and you said, I said a big elliptical can have 1 trillion stars. Now we're getting to very large scale. Is there anything bigger?
Well, there are clusters of galaxies.
And so how do they support themselves? What's going on there?
It's the same sort of thing. We're in a very, very different environment. But basically, because the galaxies are now in motion, you can put a whole cluster of galaxies together with, maybe thousands of galaxies, even for some of these really large clusters. And because they all feel each other's gravity, but as long as they don't hit each other, and they will more often in a cluster, but still we see clusters of galaxies, that whole thing will be sort of roughly stable against its own gravity. It all won't collapse into one enormous black hole.
We've gone from the smaller scale to the larger scale, and as you said, the things we see in the universe are essentially a consequence of the forces acting, and it's normally a battle against gravity, crushing everything down to be a single sort of point, right? And having black holes. We should probably finish there.
No, there's one more.
Oh, there's one more.
There's one more. The universe as a whole is expanding. It's not in equilibrium.
Okay.
So this is the interesting one. It was quite the challenge for Einstein, quite the, not for Einstein, sorry, for Newton. How do I, given that gravity is pulling everything together, how do I arrange the stuff so that everything doesn't just collapse? What Newton thought was, if I just spread everything out, there'll be no center to collapse into, so that'll work. But what we know now, it was probably true for Newton, it's definitely true for Einstein, the whole space-time can collapse. And so that's not an equilibrium state. And so the reason our universe isn't collapsing is not because it's something's sort of stable against gravity, but because it's expanding, it's just getting bigger. And so the universe as a whole is actually a kind of exception to this principle. It's not that there is something balancing gravity, it's that we're kind of escaping gravitational pull by expanding.
Oh, okay. And of course there used to be these ideas that expansion would stop and reverse and recollapse, but now we know that we appear to live in a universe quite different to that that's going to expand forever.
Yep. Anyway, that in about, 20 minutes is how you be an astrophysicist. The rest is just maths.
Excellent.